I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video where we are doing an integral calculus application with regards to work. We have to calculate the work needed to move an object from A to B. Assume one object is fixed, the other one is the one which is moving from A to B. Assume also gravitational forces involved. You know that based on the Newton's law of gravitation, we have this force is equal to a certain gravitational constant times mass of object 1 times mass of object 2 divided by the distance involved between the two objects square. We can annotate that as r square. When you're dealing with work with regards to integral calculus, your basic premise is this: work is equal to something, A to B. This part right over here is involving the distance aspect, certain function which is bringing in the force, and you are doing everything like this. Your force, your distance, and your integral comes through to give you your work, and that's the template we're utilizing for this. It's a conceptual question because you can see there are no actual numbers involved. We're looking at everything using a certain function and using a certain limit A to B. So let's bring everything into perspective. We know the Newton's law of gravitation will come in as our force component. We have here our work is equal to a certain distance from A to B. What is this question about? You have one object which is fixed, and this right here is my fixed object. You have another object which is moving, and it's a movable object. Imagine this right here is position A and it's moving here to position B. So it's going to translate and come right over here. This object being fixed. What's the work involved in this distance that it will ensue given the fact that there's a certain gravitational force involved? So how do we do it? We know we have our force component which is G m1 m2 divided by r square, and then look what I'm going to do over here. Since I'm looking here at 1, 2, 3 constants in the numerator and a variable here in the denominator, I can just make my variable r, which is what it is, and make an integral with respect to dr. There's nothing wrong with doing that. So you're calculating everything with regards to a r variable. And what are your constants? Push them out. You can say work is equal to G and then M1, then M2, and we have A to B, 1 over R squared dr. This right here is what's integrating. It's basic polynomial integral. I don't need to show you how to integrate it because you know how to do it. When you integrate it, you have R to the minus 2 plus 1 divided by minus 2 plus 1. We're looking at it from B to A. When you compute this, you know it's not hard. You have a M1, M2, your gravitational constant. You will have over here r to the minus 1 over minus 1 from B to A. When you bring all of this together, you have a minus G m1 m2, and then you will have over here 1 over r. But why don't I bring in my limits, which are my distance items? 1 over B minus 1 over A is here equal to the work involved in moving that movable object from point A to point B against a non-movable object, perhaps having a much larger mass than the object that's moving. I do not like over here the idea that I have a minus over here at the very beginning. What I can do is I can translate the minus over here and apply to the items in the parentheses and then shuffle things around. What I'll do is I'll erase this part here on the top and we'll post our final answer over there for you. Our answer is this: the work involved in moving that one object from A to B, given the fact that the force of gravitation is involved, is equal to your gravitational constant times mass 1 times mass 2, non-movable and a movable object, times 1 over A minus 1 over B. And this here is our answer, and it should be good. And that brings us here to the end of this video. Thank you.